2 through graphs of functions. We're also going to talk about some of the properties of functions. This is the notes on page 5 and 6 of the student note packet. So the pink pages 5 and 6, this lecture will match those. So let's get started. The vertical line test is how we tell whether or not we've got something that is a function. So if a graph passes the vertical line test, we can identify that graph as a function. We've got a few examples here. So A passes the vertical line test, x squared is a function. Also B passes the vertical line test, x cubed is a function. However, when we switch the parabola, x is equal to y squared in the case of example C here, we don't pass the vertical line test. That's not a function. And then similarly with D, we've got a circle. Circles don't pass the vertical line test. So D is also not a function. So just a really quick check to tell whether something or not is a function graphically. Okay, so let's talk about this. Example 1 on page 5, we've got this graph and we want to evaluate different values of this function. So what are the values of f of 0, f of 3 pi over 2, and f of 3 pi? So what we're going to do is we're going to look at these values of x on our graph, and then we're going to evaluate for y. So find 0 on the graph. When x is 0, f of x is 4. So we just write it like that. When x is 3 pi over 2, f of x is 0. And then when x is 3 pi, f of x is negative 4. That's just how we'll write those. Continuing on, what is the domain of f? So remember, domain, we're talking about the x values. So along the x-axis, what are the x values that we've got here? Well, our starting value is 0. We don't go past 0 to the left. So we start at 0 and we include 0. So I'm going to write the square bracket there if I'm using interval notation. And then our last point to the right along the x-axis is at 4 pi. We don't go past 4 pi to the right. So that's our upper bound. Again, we include 4 pi because we've got a point there. So again, I'm going to include a square bracket if I'm using interval notation. If you weren't going to use interval notation and you like it that way with the inequality signs, then x is greater than or equal to 0, less than or equal to 4 pi is another way to write that. Okay, so that's our domain. Our range then, we're talking about the y values. So look along the y-axis for the minimum and the maximum values. Now our minimum value is down here at negative 4. We also include negative 4. So if I'm using interval notation, I'm going to write the square bracket there. And then the upper bound, or the maximum value, is positive 4. Again, we include that. So you could write it this way as well. Negative 4 is less than or equal to y, which is less than or equal to positive 4. So that's how we're going to express the range. Domain, x values, range, y values there. All right, how about those intercepts? Now, I don't specify which type of intercept, so we're going to list all of them. So let's start with the y-intercepts, where the graph crosses the y-axis. We only have one, that's 0, 4. It's that first point there. How about those x-intercepts, though? We've got a few more of those. So the first x-intercept is pi over 2, 0. Then we've got 3 pi over 2, 0. And then 5 pi over 2, 0. And then the last x-intercept is 7 pi over 2, 0. And I'm going to make sure that I distinguish between x and y-intercepts if I don't ask you specifically for one or the other. All right, same graph. How often does the line y is equal to 2 intersect the graph? So graph the line y is equal to 2. That is a horizontal line at the value y is equal to 2. And then we count how many times the graph intersects our function. 1, 2, 3, 4 times. For what values of x does f of x equal negative 4? So this time we're looking for the y values that are negative 4. There are 2 of them. So 2 x values yield y values of negative 4. Those 2 are pi and 3 pi. Last question for example 1. For what values of x is f of x greater than 0? So for what values of x is our function greater than 0? So if we're talking about function values, we're looking at the y values. So we only want the values of x where our function is above the x-axis. So we only care about this part of our graph. Everything that I'm highlighting in purple is above the x-axis. That is where our function is greater than 0. We don't care about the values below the x-axis. That's where our function's negative. Now, we also want to note, I didn't ask for where it's greater than or equal to 0, and that's going to be really important when we actually start writing the final answers. So the question is, for what values of x? So we're looking at intervals here. So the first interval starts at 0 and goes to pi over 2. So we include 0 in that interval because at 0, f of x is 4. It's greater than 0. But we're not going to include pi over 2 in that interval because at pi over 2, our function is equal to 0, and we only want the interval where the function is strictly greater than. So that's the first interval. The next piece then is between 3 pi over 2 and 5 pi over 2. And again, we're not going to include those values because at 3 pi over 2 and 5 pi over 2, our function again is equal to 0. Those are the zeros of our function. So I'm going to include parentheses around 3 pi over 2 and 5 pi over 2 to denote that we don't include those in the interval. And then the last interval where our function is greater than 0 starts at 7 pi over 2, which is another 0, so we don't include that, and goes to 4 pi, which is that domain restriction. And 4 pi is going to have a square bracket because we include 4 pi in that value. At 4 pi, our function is 4. It is greater than 0. Now, if you don't like interval notation, we can rewrite this with inequalities. All right, so the first one, 0 pi over 2. That is 0 is less than or equal to x, which is less than pi over 2. And then 3 pi over 2 is less than x, which is less than 5 pi over 2. And then the last one, 7 pi over 2 is less than x, which is less than or equal to 4 pi. So you could also write it that way. Doesn't matter to me. Pick the way that you like best and stick with that. All right, so there's different types of symmetry that we're going to talk about. Two that are really important. So symmetry with respect to a line. So that line could be anything. Y is equal to x, the x-axis, the y-axis, most commonly those are used. And we call those reflectional symmetry. Anything with symmetry with respect to a point, we call rotational symmetry. So a lot of times we're going to check to see if something has symmetry with respect to the origin. And again, we call that rotational symmetry. So in this example, at the bottom of page 5, we want to determine whether the graph is a function. And if it is, we're going to find the domain, the range, the intercepts, and any symmetry it's got. So the first thing we're going to check is we're going to see if this passes the vertical line test. So example A immediately does not pass the vertical line test. So we stop there. It is not a function. Okay, so we move on. Graph B definitely passes the vertical line test. This is a function, so let's start with domain and range. The domain here, we're talking about the x values, going to range from negative pi to pi. I'm going to include both of those values because we have closed circles at both negative pi and pi. If those were open circles, we wouldn't include those in the domain. The range then is the height, right? The y values of our graph. So our minimum value is -1. Our maximum value is +1. We have points at both -1 and +1, so we include those in the range as well. All right, part B asks for intercepts, if any. So let's start with the y-intercept. We have a y-intercept here at 0, 1. That's it. The x-intercepts, we've got 2 of them. One at negative pi over 2, 0. And the other at positive pi over 2, 0. And then very last thing we're asked to do is find symmetry if it's got any. This graph, if we fold it along the y-axis, it would match up. So we have y-axis symmetry, otherwise known as line symmetry, across the line x is equal to 0. Last example like this, see, that's kind of nice again. It doesn't pass the vertical line test, so this is not a function, and we don't have to do anything else for that problem. So if you turn the page to page 6 in the student note packet, we've got at the very top some definitions here. So even versus odd functions. A function is even if for every number in its domain, we also have the number negative x in its domain, right? So the way that we prove that algebraically is if I take x and I replace it with negative x in the function and simplify, and we get back the original function, we have a function that is even. Another way to look at that is if we start with the point xy, then an even function should also have the point negative xy. We can also apply a similar rule for odd functions, so it looks just a little bit different. If I replace x with negative x in an odd function, simplify the equation, and we get that original function, but times -1, then we've got an odd function. So in a different way, if we start with the point xy, then the point negative x, negative y should also be on that function as well. If none of the above satisfy, so we replace x with negative x, we don't get back the original function, or we don't get back the original function times -1, we get a combination of kind of two of those things, then it's neither even nor odd. We can also determine whether a function is even or odd if we're looking at a graph. An even function is going to have symmetry with respect to the y-axis. An odd function is going to have symmetry with respect to the origin. So that's point symmetry. It's a little bit harder to see, but we'll take a look at an example. Okay, so we want to take a look at the graphs and determine whether we have a graph that's even or odd. I've got the rules up here in green. So let's start. Example A, whether or not this is even or odd. Let's take a look at the symmetry here. A has symmetry with respect to the y-axis. If we were to fold this along that y-axis, it would match up. So we say this is an even function because it has symmetry with respect to the y-axis. Okay, if we take a look at B, B does not have symmetry with respect to the y-axis, so it's definitely not even. Let's talk about odd. An odd function has to have symmetry with respect to the origin. So if we take a look, the origin is here in orange. This doesn't have any symmetry around the origin either. So this is neither. This is neither even nor odd. It does, however, have symmetry. It has point symmetry, but it's not on the origin. This is shifted up like that. So still neither even nor odd, but nice to see the symmetry there. The last example here, C, this does have symmetry. This has symmetry with respect to the origin. So here's how you find whether or not a function has symmetry with respect to the origin. If you were to fold this graph on both the x and the y-axis, so take a piece of paper with this graph on it, fold it up along the x-axis, you get something that looks like that. And then if you fold that along the y-axis, and if that matches, then it has symmetry with respect to the origin, and this is an odd function, right? So a little bit harder to see. I think the easiest way to visualize an odd function with symmetry with respect to the origin is just fold it along the x and the y-axis and see if it all lines up. Algebraically, a little bit different. So we are going to take a look at replacing x with negative x and seeing what happens. So in this example, I'm going to take x and we're going to replace it with negative x, and we're going to see what happens to x. Now I'm going to make sure that I include parentheses everywhere so I don't drop a negative on accident. Now negative x to the fourth power, that's just positive x, and negative x squared is also positive x. All right, so what happens here is we get back exactly the same function that we started with. So this is even, okay, by the definition of even and odd. How about this one? We are going to replace x with negative x and g of x and see what happens. Again, I'm going to make sure I include parentheses there. Now, what happens here is negative x cubed is negative x cubed. And when I compare this to the original function g of x, it's not the same, so it's not even. But it's also not g of x times -1, because if g of x is multiplied by -1, every sign would change. We should have a +1 there. So this is neither even nor odd. And then the last example for h of x, we're going to replace x with negative x. What happens when we do that is we get negative 2x cubed plus x. Now, negative 2x cubed plus x, it's not the same as what we started with, so it's not even, but it is h of x times -1. Both signs changed there, so that means this is an odd function. So I've been using interval notation in the last couple of lectures. This is kind of here to solidify your understanding of interval notation. Anytime I'm using parentheses, that means we're excluding those values. That would be a strictly less than or greater than symbol there. Anytime we use square brackets, that means we're including those values. That's where we would have on a graph a closed circle. The parentheses would represent an open circle. Okay, so inclusive versus exclusive. Pause the video if you want to take a look at the examples there. Last example, example number 4, back of page 6 on the student note packet. We've got this function, we've got this graph on the right, for you guys it's on the left, and we want to know, is the function increasing on the interval -4 to 0? So when we're talking about interval -4 to 0, that means I'm looking along the x-axis. So -4 to 0 would mean if I were to draw a box, right, including only those values -4 to 0, is our function increasing? So within that box, look at the graph. Are we moving upward? The answer is yes. Our slope is positive at every point between -4 and 0. Next one is f decreasing on the interval 2, 6. So if I were to draw a box along the interval 2, 6, so 2 and 6, if we look at our function inside of that box defined by that interval, is the function strictly decreasing? Now, the issue is this flat part here. The answer is no, because the slope between 2 and 3 is not decreasing, it's not negative. The slope is 0 on the interval 2 to 3. Okay, so we can't say it's decreasing because it's not negative. C asks us to list all the intervals where our function is decreasing, so let's take a look. Going from left to right, we have decreasing values for the slope here, negative values for the slope between -6 and -4. We're not going to include either of those because at -4, the slope would be 0, and we don't know what the function does to the left of -6, so we can't make any assumptions there. All right, what is the next interval where our function is decreasing? Well, the next interval is going to be down here from 3 to 6. So I just use interval notation. You could also choose to use inequalities if you'd like. The first interval would look like that, and then the second interval would look like this. All right, next we want to list the intervals where our function is constant. So we're looking for flat lines here, where the slope is actually 0. So the slope is 0 here between 0 and 3. That's how I'm going to list that. And then we don't include 0 and 3 in that either, because at 0, we start decreasing to the left of 0. So it's not the same on both sides. Same thing over here at 3. To the left of 3, the slope is 0, but to the right of 3, we start decreasing. The slope is negative after that. And then the last question lists the numbers where a function has a local maximum. So we're looking for local maximums here. Our function is at its maximum, also along where the slope is 0. So between 0 and 3, on that interval 0 to 3, now, in this case, we are actually going to include 0 and 3, and the reason is the question is talking about maximums. We are at a maximum when x is 0, we're at a maximum when x is 3, so we can include 0 and 3 in that answer for E. All right, that is it for 2-3. Get started on your homework.